Hello, I'm Ardit. I'm the lead developer at JSparrow. You can find me on LinkedIn. Some people call me DT, and that's why my LinkedIn profile is DTY. In this talk, I will talk a little bit about refactoring. I will focus on Java. The previous speakers did not have any specific language, but I will mainly focus on Java, even though some of the concepts are the same for other programming languages too. I will have a look at some features that were introduced lately in Java and why should we use them, and is it possible to automatically transform the old language construct into this new language construct, so to make use of the new features, and also what are the benefits of making use of those features, like are there performance benefits or are there security benefits and similar things. Yeah, at the end, I will have a look at the challenges that one might face when deciding to write a tool for doing automatic code transformation. And when doing that, we also should keep in mind some computability theory. Okay, so a general definition of refactoring we have already seen. Mr. Cargill already talked to us a lot about it. However, in this talk, I will not focus on architectural refactoring, but I will focus more on low-level refactoring, like changing code snippets and fixing code smells in an automated manner, and yeah, similarly. These are sometimes also called micro refactorings. The first thing to keep in mind is whenever you decide to do some changes in the code, it is absolutely necessary to have a test suite that you can trust. So should you decide to make a change in the system, you should also have complete faith on your test environment that if you break something, they would catch it. That's very hard to have, but it is very important to make sure that the impact on the functionality to be zero or as minimal as possible. So having that in mind, when deciding to refactoring something, at first we should define a specific goal, which should be cohesive and should have a specific purpose for improving a certain aspect in the system. And then we go ahead and change the code to achieve the defined goal, and then immediately we test. And we repeat those steps until the goal that we had in the beginning is reached. Another question is why and when or how often do we have to do it? So refactoring is also part of the daily development work. You might have heard a quote about programming that a software is never written, it is rewritten. So every time we implement something, then we never stop at the first idea that we get. Another quote that comes into my mind is, nothing is more dangerous than an idea if that's the only idea that you have. So as part of daily work, we always used to come up with better solutions and find efficient ways to, or elegant ways to implement certain functionalities. Another important topic that doesn't actually depend on us is that the third-party libraries and the language that we are using are evolving continuously and very, very fast, actually. So if we have Java in mind, for example, there are so many features that have been introduced lately in Java. So the new release cadence, so 6-month release, is turning out to be very successful in regard to the new language features that are introduced into Java. So even though Java is one of the most senior languages in the market, they are introducing so many modern language features, let's say, into the system. Yeah, recently Java 16 was released, and with Java 16 we saw, for example, records, pattern matching, for instance, of while sealed classes are still on the preview feature. They will be there soon. In Java 15 we saw text blocks. That's also an interesting feature for writing string literals without having to escape all the special characters and so on. In Java 14, I love this one very much. We saw switch expressions. So switch are not only statements anymore, but are also expressions for computing a value and storing it somewhere. We also don't have to write all those nasty break statements after each case. And also the compiler is smart enough to evaluate if all the cases are exhausted, so we are not forced to write a default statement. Earlier in Java 10, we also saw local variable type inferences. Sorry, I'll drink some water. Which also help on making code look smaller and shorter while letting the compiler do the rest for deriving trivial information. Having said that, let's have a look at the Java records and what they actually would bring us. Well, a record is, let's say, like a holder for some data values, and it is immutable. That helped especially in defining domain models. So we all used to solve those nasty definitions in the domain models that had so much boilerplate code. Sometimes even developers go to cut out corners and avoid writing important methods like toString equals or hash code. With records, all this boilerplate code would go out, and we can define a similar user model, let's say, by writing one single line of code. In the records, you can, of course, add more methods to it, but you cannot add fields. Java records already extend one class, which is the Java lang record. So there is no possibility to extend another class. So if you write extends in the record definition, then you would get a compiler error. You can also add more functionality to the constructor of the record. This is also called the canonical constructor, which defines all the components that the record would represent. So far, I only talked about the syntax of the records, but this is not only a syntactic sugar for classes. One of the main criticisms in Java is serialization and deserialization. So let's say we have already converted, serialized an object into a byte stream, and we are at the point that we have to convert that byte stream back to a Java object. The way that Java used to do it with ordinary objects is, read the byte stream, find the class description, call the default constructor of the parent of the class, which in most of the cases is the constructor new object, and then read the fields in the byte stream that should be stored into the state of the object, and use the reflection API for actually setting those fields. So the problem with that is the constructor of the object that is being created is avoided. And should the constructor contain validation logic about the values that the fields need to have, then those validation steps would be skipped. With records, this works a little different. Since records have a canonical constructor, there is no way to construct an instance of a record without invoking the canonical constructor. And for this reason, when doing the deserialization of a byte stream into a record, first, the deserialization process reads the components that should be stored in the record. And only afterwards, after all the components are prepared, then it uses the canonical constructor of the component of the record to actually construct an instance of that record. And yeah, in this way, we do not avoid invoking the canonical constructor or the constructor of the record, but this comes with the cost of being unable to have circular references in the records. The reason for that is, yeah, before invoking the canonical constructor, all the components that should be stored in the record have to be first deserialized. And we would spin into a circular problem if we would try to deserialize a component that actually depends on the record where it has to be stored. And not only that, another interesting feature about records is that the equals hash code and the toString method are implemented in a nice way in the bytecode level. So here we see the implementation in the bytecode level of the record equals method. And it's very simple and very elegant. And we see in line number 2 that there is an invoke dynamic called. This invoke dynamic is an opcode which was introduced in Java 7. And the purpose for introducing the invoke dynamic was to add support for dynamically typed languages that run on the JVM, like JRuby. Afterwards, in Java 8 and 9 and 11, the invoke dynamic started to also be used in implementations of the Java language construct itself. It first started with lambda expression and then with string concatenation, and now we also see them in the records. So the idea behind invoke dynamic is to shift some code generation logic from the compilation time to runtime. So yeah, and the way that is done is as soon as the Java virtual machines sees an invoke dynamic invocation, then it calls a method called bootstrap method, which is responsible for generating a call side. The call side then contains a method handle and a condition which encapsulates the code that will actually be executed. So this first time that JVM sees the invoke dynamic could be rather slower, but then after the call side is generated, it contains all the information that we need for executing the target method, and this call side then will be reused as often as it can should the invoke dynamic occur again in the execution flow. Yeah, this is like a tricky topic, it would be enough for starting another talk only on Invoke Dynamic. But the overall idea is shift the generation of the bytecode from compile time into the runtime. And this has the first advantage that should the JVM decide, or the if in a new Java version there is a better implementation of certain features, then the users would not have to recompile the code for making use of the new implementation of the bootstrap method or so. The next topic I want to talk about is string concatenation. Up until Java 8, the concatenations of strings in Java were performed using the string builder. Here we see a very small method that concatenates only two values, and well, actually it concatenates a string literal with a string variable, and the bytecode generated for such a simple method is rather large. So we have first the initialization of a string builder, and then we load the variables one by one to, and then we use the string builder to append them all together. In the end, we call the toString method in the string builder to get the actual result. If we go to Java 9, this changed completely. Here we again see an instance of where Invoke Dynamic is called. And what Invoke Dynamic does in this case is it defines, yeah, it calls the bootstrap method, and it, which is called make concat with constants, and it passes as parameters the signature that represents what is the function that would be, or how does the function that would concatenate the strings look like. Here we see only one parameter for the actual string variable, but there is no parameter for the string literal, because the bootstrap method is able to capture the constant and string literals, and we don't have to pass them as parameters. And the return value would be a simple string. Additionally, a parameter to the bootstrap method is also the recipe, which can be seen as a string template, which contains together constants and placeholder for variables that would be concatenated with each other. The default implementation for actually performing the concatenation in Java 9 is not the string builders, but it is something similar, which directly manages the bytecode arrays and puts together the values that have to be concatenated according to the recipe that is provided. I already mentioned it before. Lambda expressions are the first feature in Java that made use of the Invoke Dynamic opcode. An alternative would have been to actually implement lambda expressions as anonymous classes. So a question would be, how much better is a lambda expression which is implemented with Invoke Dynamics compared to simple anonymous classes? The first thing is, if a lambda expression is never used, then it hardly occupies any space in the Java heap. On the other hand, anonymous class, as soon as it is created, it will reserve some memory in the Java heap. The next thing is the bytecode that is generated for executing lambdas that do not capture any variables from the context is a bytecode that will never change. So the JVM would simply store it or cache it somewhere in the memory. And every time that that lambda expression would be invoked, then it doesn't have to recalculate all the bytecode that would represent the method for containing the logic of the lambda expression, but it would immediately go and call it, and this would be a lot more efficient than creating a new anonymous class every time we execute it. On the other hand, if the lambda expression is capturing some value from the context, as we see in the second lambda example here. So the threshold here is a variable which is declared before the lambda expression is defined. In that case, depending on the value that the variable has, the method handle which represents how the lambda expression will be executed have to be reconsidered. And in that case, the performance of executing lambda expression could deteriorate to the performance of executing a normal anonymous class, but it never goes worse than that. So in the best case scenario, we get an execution which is extremely faster than normal lambda anonymous class. And in the worst case scenario, the performance of a lambda expression would be as bad as the performance or as good as the performance of a normal anonymous class. And actually lambdas that do not capture variables from state are quite commonly used. So yeah, we see often examples like don't do anything with the variables in the context, but just increment or define a function for incrementing a value or for computing a new value that does not depend on any of the variables in the context. And there is more to that. So it's refactoring has a larger scope than only replacing the old language constructs with new language constructs. And here we can have, for example, security issues or security holes that we have to close in the system. We might want to improve the system loggings, or we might simply want to have better or to meet some coding conventions in the software. Another example would be a third-party library that we use suddenly introduces a new version, and we might want to catch up with that. For example, let's say we want to transition from JUnit 4 to JUnit 5. What do we have to have in mind? The first thing is in Java 5, in JUnit 5, the test annotation contains no annotation properties. Instead, we have assertions that would perform the same or would bring the same functionality, maybe even in a better way than the annotation properties. So for example, expected exception can be simply replaced with assert throws, or the test timeout annotation property can be easily replaced with assert timeout. And this makes also the test code more readable, as we can define specifically where we would be expecting a certain exception to happen, or which part of the code we would want to measure its timeout. In addition to that, most of the annotations in JUnit 4 have a unique correspondence in JUnit 5. For example, the at before, at after, at ignore, and category annotations have an equivalent counterpart in JUnit 5. So if we want to transition, we just have to replace those annotations with the new annotations. Similar is for assertions and assumptions. The assertions in JUnit 4 are defined in org JUnit assert. On the other hand, on JUnit 5, assertions with the same or with very similar signature are defined in org JUnit Jupyter API assertions, and it's the same for assumptions. It's more problematic for transitioning rules and runners, so JUnit rules and JUnit runners into JUnit 5. And that's because in JUnit 5, there is no support for, or there is very limited support for JUnit rules that we used to have in JUnit 4. To do that, so should we decide to anyway transition, then we would have to re-implement the rules that we have defined with extend with and register extension. Security is the last topic that I wanted to mention, and that can be subject to refactoring. And most commonly, we have experienced cases where dynamic queries were concatenated with user inputs, and that's clearly a security hole. The alternative to do it would be to make use of prepared statements, meaning parameterized queries. In this case, for example, it would be rather straightforward to convert the string the string representing the query in a parameterized query, and use a prepared statement rather than a simple statement for executing the query. The changes to the down actually in the code are very minimalistic. So we replace the parameter with a question mark, and we insert one more statement for setting the potential user input in the parameter placeholder. Additionally, the Java SQL statement is converted into a prepared statement, and this is also not very problematic since the statement is already a parent of the prepared statement. So should the variable statement be only used for the purpose of executing the query, then such a transformation would be feasible and would not cause any other problems in the rest of the code. Similarly, we would have other topics related to security, like C-link classes that will come soon. It's already a preview feature in Java 16, or other more simple and more common examples for like making better use of random number generators, or making use of the more secure encryption algorithms that actually also in Java we have very often deprecated encryption algorithms and introduced new encryption algorithms that are very important to work with. The problem is that with the should we decide to change an encryption algorithm that might cause side effects that are unexpected on clients of the software. Having mentioned all those language features and transformations, the question would be how much possible is it to make a program that would perform refactoring in an automated manner, and how do we make sure in general that the code that we had originally behaves the same as the new code. An example would be, let's say we have an anonymous class and we want to transform it into a lambda expression. Yeah, we have to do quite a lot of checks for the variables that are used in the anonymous class, for immutability state, and so on. The Java language specification would be a good help in this case for finding out all the properties that a certain language construct has and the restrictions that an alternative language construct could impose. So to answer the question about preserving functionality, let's have a look at what the computability theory tells us about. I mentioned before that testing is important, but if we consider a program as a function that maps an input state to an output state, then having having a complete coverage of the tests would mean that we would have a single test case for every possible combinations of the variables in the input state. And that is practically impossible because the input state or the number of the input states would grow exponentially with the number of the variables that we have in a program. And we have endless endless variables in a program, which means practically we would have to write infinitely many tests. What we have instead is a program that gets two other programs as parameters and answers the questions if those two programs would always terminate on the same state when starting in the same state. And unfortunately, this is impossible to write because this would be similar to asking the question, having a program and input state, does the program terminate on that state or not? And this is the well-known halting problem, which is shown to be undecidable. And not only that, a famous theorem on the computability theory says that all non-trivial semantic properties of a program are undecidable. This means, or these usually refer to behavioral properties of the program, meaning other examples would be for can a certain line of the code be reached, or would the variable ever get a certain value, and so on. They are all behavioral properties of the program, and in general, they are all undecidable. The good news is that when we only do syntactic transformations on the program, on a code snippet, then we are not too interested on behavior, on semantic properties, but we are more interested in syntactical properties. And to analyze syntactic properties, it's enough if we parse the code into an abstract syntax tree, so in a data structure that represents a certain code, and then walking that tree, we can find out about all syntactic properties that the program contains. And to do that, we would make use of some language parsers. There are many open source language parsers out there. The one that we use in JSparrow is Eclipse JDT. It's a very beautiful piece of technology. It allows you to parse the code. It has an integrated compiler. So with the help of that, you can also verify if the code contains compilation errors or not. It allows for making manipulations on the code by changing certain nodes on the abstract syntax tree, and also allows for storing the changes before committing them into the original code, so that you would have a second chance on showing the users the changes that you made in the code before you commit them into the original sources. There are other alternatives like Java parsers, which is integrated into the IntelliJ IDE. This is a very powerful piece of program as well. It almost allows the same functionalities as we see in JDT. Another alternative would be using until R. This is language independent, and users can define their own grammars for a language. It is especially useful for people who work with domain-specific languages. So I already talked a little bit about it. So once we get a parsed code into an abstract syntax tree, then we have to use a visitor for the visitor pattern for visiting nodes in tree order, and discover nodes that would be of interest. For example, we would stop at visiting anonymous classes and look for what is in the what methods are implemented in that anonymous class, and then see if there is only one method implemented and no other methods or fields defined in an anonymous class. Then we would also have to look for, let's say, variables that are used in the single method that is implemented in the anonymous class, and if all those conditions would pass, then we would generate the lambda expression and simply get the code that occurs in the body of the method in the anonymous class into the body of the new lambda expression. And then we would simply replace the existing anonymous class with a new lambda expression without affecting the rest of the code. After that, we have to still make sure that the code is valid by checking, let's say, for the variables that are non-effectively final and would be captured by the anonymous class that is legal for anonymous classes, but is illegal for lambda expressions. Or, for example, checking if if there is a variable defined in the anonymous class that has the same name with another variable defined in the external scope of the anonymous class. Since anonymous classes will define their own scope, that would be perfectly fine, but should we decide to replace that with a lambda expression, that would cause a naming conflict. Yeah, and in the very final step, we would simply show the changes to the user and let the user choose to commit it or not into the original source base. Yeah, to summarize, refactoring is fun, would improve a lot your code quality, and very often can be also automated. this is all I had to talk with. I wonder if there are questions.